Okay, here we're going to talk about feature attribution in deep neural networks. Before I get into what that is, just note that the lecture notes I'm going to go over are here. The link to this financial education website will be in the description under courses, MLAI, and feature attribution using Captum. So, a little background on deep neural networks. So, these are often used by businesses to predict. Deep neural networks are heavily used by tech companies which are in which they get a lot of revenue from advertising, right? So they'll use a deep neural network to predict what you're most likely to click on next, or in auto lending, I might use a deep neural network to predict who's going to default or be delinquent. But so for a lot of these business cases, right, particularly on the tech company and advertising and so forth, what's going on is we're feeding a lot of data about you and feeding a lot of data into the model and trying to make a prediction. And what I want is my prediction to be accurate. I don't particularly care how the inputs affect the prediction, right? I just want my prediction to be accurate. So a lot of companies are just saying, okay, well, I'm going to feed as much data into this neural network as I possibly can, make some prediction about, again, it could be usually, advertising what you're going to click, or Amazon what you're going to buy next. And my only metric is my out of sample prediction error, right? However, many businesses, but also heavily in sort of academia and research, we don't just care about the prediction, right? How accurate the prediction is. We also care about how the inputs affect the output, right? So I'll go back to sort of auto lending, right? It would be useful to predict who's going to be default and be delinquent on an auto loan. And if I just had a model that predicted very well, I'm happy. However, we could also be interested in, well, why did they? What is more likely to make them default? So in other words, how is debt to income related to default? And the reason being is, well, if we originate auto loans, we can change our lending policies if given this relationship. So if I say debt to income has a really significant, I use a logistic model and I calculate debt to income has a really big impact. I can look at thresholds of debt to income that would really cause increases in delinquency, and then change our lending policy, change our origination policy. So what we'd really like to do is be able to do this feature importance, right, in deep neural networks. So the idea of this is, what we want to do is, in a logistic model, I can get out of how important debt to income is. What I really want to be able to do is, in a deep neural networks, which are really useful, also be able to get how important this input is. And so there's a fairly new library called Captum, right? It's part of the PyTorch sort of ecosystem. Here's its GitHub. That the purpose of it is to do this feature importance in deep neural networks. So tell us, how important these particular inputs are. So what I've done here is I've gone and created an example. So I use a different, I'm creating an example on FTR option, right? So valuing financial transmission right options via deep learning. So the idea here is, I want an option pricing model. Another example of where we want feature importance when we're talking about investments is, you could have an option pricing model that's a deep neural network that really predicts option prices well. However, if you manage an option book, right, then the Greeks become very important, right? Delta, gamma, theta, so forth. So the idea is, how sensitive is my option book or this particular option to changes in the underlying stock or changes in time and so forth. So these Greeks. So what we're going to do is we're going to sort of get feature importance on an option pricing model, which is going to give us kind of these Greek values. But however, what I'm going to do here is an FTR option. Financial transmission, right? These are really interesting options. You don't see them much there. You see them a lot in industry. This is electricity trading, not so much in academic research. But they're really interesting. It's basically it's a derivative that allows to hedge for congestion in the network. What you can think of this FTR option is, it's an option to transmit from one point to another on the electric grid. So So this is kind of going to be a little bit of a unique option, specifically because this is the stochastic process that electricity, that we often use to model electricity. This is different than standard geometric Brownian motion. This is standard geometric Brownian motion in this term here. However, the mean term exhibits mean reversion, with a mean reversion speed of kappa. So to value this option, what I've done is I've gone through and used Monte Carlo to create a bunch of option values. So I generated a random risk-free rate, within bounds, random volatility of the electricity. This is going to be electricity at 0.1 and 0.2. All right, this is in FTRs. This is called the sink and the source. I'm going to transmit from here to there. The correlation between the prices at the sink and the source, the mean reversion, right, of the sink, the mean reversion of the source electricity price. So this price process I have for the 2 points, again, sink and source. The source is where I'm transmitting from, the sink is where I'm going to, right? And then I have, there's more like the price that it starts at, the mean price. Electricity generally fluctuates around a mean. So here, this would be like $25 per megawatt hour. And then, I simulate a bunch of these and I simulate an option value. And then I simulate a bunch of these and it gives me an option value. These are path-dependent options. So the idea is I have to simulate the entire path. So anyway, I get a bunch of option values by Monte Carlo, and then I just use this in PyTorch, simple sequential deep neural network to value the option. So what's going on here is, I have 10 inputs, a bunch of hidden layers, and then, one output, which is the option price. The interesting thing about this is I can train this deep neural network and I can just send it to you and then you can use it, right, for inference. So, PyTorch, you might know, but you can save and load models, right? So once you train this model, I might train this model for a long time, and then I can just share it, and other people can use it for an inference, which would be like just known as a forward step. So in this notebook, I'm just loading a pre-trained model that I have, and here's the prediction error. So you can see here is here is what I'm trying to predict, and here's my prediction for it. And you can see it's the option model works fairly well, right? I forget how many times I trained it, but has fairly low this is of course out of sample, right? So it's fairly low out of sample prediction error. The idea is I train it and then I feed in a bunch of new data that gives me the actual option price, and this is the option price from the neural network. So getting into the point of the video is feeding this into Captum. Let me see. This is going to be just a larger version of that chart. I can get some feature importance. So the idea here is we'll start with volatility. So the idea is the more volatile the electricity price is at the sink or the source, the higher the option value, and we're seeing that here, right? Generally, the higher. It's interesting. These are different feature attribution methods, right? So I'm doing a bunch of different feature attribution methods. So this makes sense. Generally outside of this gray, which is just weights, but we see a positive correlation here, positive correlation here. We see a positive correlation with the risk-free rate, which is what we should expect. This is a little different. You won't see this much in Black-Scholes, but the correlation, because there's no correlation, now we have correlation between two series, right? In Black-Scholes, you have a stop price and then a strike price, which is a strike is a constant, so the correlation is 0. So you never see this correlation, but in general, this is a little bit interesting. The higher the correlation, the lower the price, right, for the option. It's a little bit muddy because if the correlation gets the option becomes worth very little if the correlation is 1 or -1. So if it approaches 1 in absolute value, the option has more value as it goes to 0. But because the correlations are generally positive, you see this relationship that correlation goes up, option value goes down, which is absolutely spot on. Similarly, the rate of mean reversion, right? if the option reverts, I mean the electricity prices revert to the mean quickly, you get a lower option values, right? So this everything here is as we would expect. Let me kind of scroll right here. Right, this is going to be the where we're transmitting to. So the idea is if that's higher, right, and where we're transmitting from is lower, then the spread is wider and the option is worth more. And similarly for mu. So in sum, this feature attribution works very well, right? So I did this to look at Captum, and so we can sit here and say, okay, well, I know theoretically what these should be beforehand, and I want to make sure that they are right. And yeah, these make perfect theoretical sense. So this is a very useful library. Like I said, you know, here we're kind of getting an idea of Greeks, but now, given this, I'm really interested to go in and say, okay, let me give a probability of default model or a prepayment risk model, you know, where this might be useful. So, you know, we have models that calculate the probability that you're going to prepay your mortgage, you know, based on housing price, based on what you know interest rates are doing, and so forth. So and I've used like logistic models and so forth for this, but it'd be really interesting to maybe gather some data and do some feature attribution there. But yeah, so this package is sort of bridging the deep neural network. You know, the ability of deep neural networks to do very good predictions, and then adding to that feature attribution that we've been missing thus far. Great. So if you get a chance, give Captum a try, and have a great day.